Okay, so we've got our final exams coming up, but let's talk about, there'll be a homework due on Wednesday at 7 a.m. and there will probably be a homework due on Thursday at 7 a.m. Okay, because we're going to talk about nuclear chemistry and I want you to have some practice problems for nuclear chemistry. Let's see. So you got final exams on Thursday and Friday, starting at 8:30 a.m. in here. Okay, that you can choose which of those you want to go to. If you're not, yours is officially the one on Friday. If you're planning on going to the one on Thursday, please send me an email so that I have enough tests. Okay. I had somebody ask, you could also take the final exam on Monday, 2 to 5 p.m. in the Gen Chem lab. All right, that's where I'll be giving my biochem exam, and so, but you definitely have to let me know for that one. Well, you can let me know. You could just show up, and then what I'll do is I'll walk across to my office or down the hall and find another exam. Okay. But it won't be as disruptive to do that, at least for you. Questions? All right. But let me know if you're planning on not taking it at the regular time, and then I'll be able to better adjust. Yes.
So I'm confused. I know that tomorrow is a Friday schedule. So do we have homework due tomorrow?
That's a good question. So tomorrow is Friday. You do not have a quiz. Okay. That would have been fun, but not for me. But I'd have to grade it. So tomorrow is Friday, so you need to come to class tomorrow. So that's what's going to happen with that homework. I'm going to have this homework for today is going to be due on Wednesday, and then tomorrow we'll have lecture, and that's going to be a homework that's due on Thursday. Okay. Any questions? Okay. All right, so then today what we're going to do is we're going to finish off talking about electrochemistry. We're going to be talking about electrochemical cells. All right, so electrochemical cells. Are devices that are going to either produce or consume electrical energy. All right, so in terms of a device that produces electrical energy, we can think about batteries. And we're going to spend really most of today talking about battery-like things. And those are called voltaic cells. All right, and so these are types of electrochemical cells, but what these cells do is produce energy. And they produce energy by separating the cathode and the anode and making the electrons run through a wire. I'm sorry, did I say cathode and anode? The oxidation and reduction half reactions. All right, so what you're doing here is we have an oxidation reaction, we have a reduction reaction. The thing that's oxidized gives up electrons and they go to the thing that gets reduced. But if you separate those two and make the electrons run through a wire, you can use those electrons to do work, okay? And where work might be, work is things like turning on a light bulb, running a motor. So let's go ahead and look at an example of one of these. This is kind of a classic example. All right, is this big enough? Can everybody read all the letters? Okay. So what we've got here is this is an example of a voltaic cell. And there are various things on here we want to be comfortable with. So we have, on this cell, we have electrodes. It's a bunch of terminology we're going to have to learn. Electrodes are the locations, they're the surfaces on which the reactions occur. All right, so these were the surfaces where we have the reactions occur. In this example, so if we call these electrodes, our electrodes are, we've got our zinc in this reaction. What we've got happening is zinc is going to react, it's going to become oxidized, and it's going to give its electrons to copper, so copper becomes reduced. What happens is we have that oxidation reaction occur over here. The reduction reaction is separate here, and so the electrons that are given up by zinc have to run over here to get to the copper, so that copper can then be reduced. And when they run from here to here, you can make them do work. So here you can make them run through a light bulb and light it up. All right, so we have two types of electrodes then, or two types of systems at least. We talk about anodes. Okay, anodes is where anode is where oxidation occurs. So we'll say the electrode where oxidation occurs. The cathode is the electrode where reduction occurs. All right, so we've got the anode and the cathode here. These terms get used. You want to be able to keep the two separate, the two distinct, or keep them, remember which is which. And the way I've always done this is, I've got anode and I've got cathode, right? Those are alphabetical. And I've got oxidation and reduction. So they're both alphabetical. So O comes before R and A comes before C. If that works for you, great. Over my lifetime, I've accumulated too many of these and they stopped working at one point because I started getting confused. But this one I've actually managed to hold on to. All right, the final thing we want to talk about here in terms of one of these electrochemical cells, one of these voltaic cells, is we want to talk about a salt bridge. So the salt bridge is, it's a conductor or something. It's something that contains spectator ions, right? We have this reaction going on here, but these sodiums and these nitrates aren't doing anything in terms of the oxidation or reduction. They're not becoming oxidized, they're not being reduced, but they can move to balance out the charge. So the salt bridge contains spectator ions that can move to balance charge. All right, so what's going on here is something that you probably don't have a good feel for yet in your chemistry career, but it takes a ton of energy to separate charge. All right, so you never go into the chemistry stock room and pick up a solution that has excess positive ions in it. There's always negative ions in there to balance that out. You never go and pick up some solid and it's got more positive ions. That solid has more positive ions in it than negative ions, okay? Because it takes a lot of energy to do that. In fact, I know a lot of you are probably interested in biology for various reasons. In fact, if we think about cells, your nervous cell, right? You think about signals that go with your nerves. What happens is your nerves spend a bunch of energy, and your other cells spend energy doing this too, but they don't use it for necessarily the same thing. Spend a bunch of energy taking, let's say that's a cell membrane. They spend a bunch of energy making sure there are more positives on the outside than on the inside. And when I have a nerve impulse that goes down my arm from my spine here to make me do something, what's going on with that nerve impulse is that it's letting these positives into the cell, and it's letting some negatives out of the cell, so that we end up with a change in what we call potential. All right, a change in potential. If there are more positives outside, they want to come inside, right? Because positives are attracted to negatives. And so what you have is you have a change in potential. Up here on my arm, I have a change in potential here, and then it gets sensed right here that something changed, and so it lets some positives in, and so the nerve, the impulse goes down a little bit, and then here it senses that, hey, something changed over there, and so the nerve impulse goes down a little bit more. I'm exaggerating how far, but it's very fast, actually, obviously, because otherwise we would be moving slower. Questions? Okay. To give you a feeling, I'm going to erase this, but to give you a feeling of how much energy we're talking about here, 25% of your resting energy is your cells doing this, is them pushing positive ions out of the cell and negative ions into the cell. Okay. Mostly it's pushing more positives out than they push in. If you ever take biochemistry, we'll talk about it's one transporter that's like 25% of your resting energy that does that. Okay, questions? All right, then I want to introduce one more thing here for this cell. So chemists are lazy. I hope you've been sort of getting a feeling for that. And we don't like to have to write lots of things. And so what we have is we have a shorthand for electrochemical cells. So that's called a cell diagrams. It's not the same as what a cell diagram might be in biology. A cell diagram is a shorthand used for describing electrochemical cells. And so we have this reaction right here. All right, we've got this reaction going on. I'm actually going to write these half reactions out. We're going to add them up to make the full reaction, which is not what I'm doing here. Actually, let me do the cell diagram, but then we'll add these things together. All right, so what I've got is I'm going to start with the anode. I'm going to start with oxidation, right? It's the beginning of the alphabet, so that's a good place to start. I'm not making that up. You start with the anode. So I've got zinc here, and that zinc gets oxidized, right? So I draw one line there. That line's supposed to talk about, in your book, it'll talk about it being a phase separation or something like that. I'm not going to worry about that. This is just the reaction that's happening. And then they like to say, here's my salt bridge. They'll call that the salt bridge in terms of that, but okay, fine. I don't know that it helps picturing it to see it as the salt bridge. Do as you will. And then the other side half reaction is copper being reduced. So copper plus 2 going to copper solid. That's aqueous. And that's how that's my reaction. I've drawn that out. So if we had to, here we have 2 electrons, right? We're about to draw this reaction out, and we have 2 electrons transferred in each, so it's a 1-to-1 ratio, right? If I add these 2 reactions together, I'm going to add this to this. All right, so what that's going to give me is it's going to give me, I'll just add everything up here. So I've got zinc solid plus copper 2 plus, right, aqueous. All right, plus 2 electrons right there. Goes to make me zinc 2 plus aqueous plus 2 electrons. Right, there's my 2 electrons on that side, plus copper solid. All right, and the way these things add up, I have 2 electrons here, 2 electrons here, so I can just cancel those 2 electrons and I'm done. I don't have to multiply anything by anything else. All right, but if one of these was a silver, and we'll see silver in a bit here, I'd have to multiply to make the electrons cancel. When I write this, I don't put that multiplication in at all. I'm just showing the basic cell, writing as little as possible. That's the way you could think about it. I thought I hadn't added enough creamer to my coffee, but apparently just wasn't mixed. I'm working on my sugar high right now at the bottom of the coffee. Okay, so questions so far. We're going to practice we're about to practice this stuff. But what I did want to show you is, so I'm saying it's like a battery, right? This doesn't look much like a battery. It's actually a lot like your car battery, though. Your car battery it's a bunch of sulfuric acid, and you have separate chambers where you have lead strips sitting in that. And some of those chambers you actually do the anode reaction, and some of those chambers you do the oxidation, and some of the chambers you do the reduction. So there are 2 different reactions that can happen with those lead strips and sulfuric acid. So that's how your car battery works, and it recharges over and over. And I assume the lead eventually kind of wears out. But this is very much like your car battery, but most batteries, when I say battery, you think about something that looks like this, right? You've got a positive end and a negative end, and it's solid, right? It's not liquid, so that if it breaks open, it won't leak all over the place, although they do kind of leak if you leave them around too long, right? But that's gross. Throw them out, don't touch them, wash your hands. Touch and wash your hands afterwards. But we've got reduction half reaction here, right? We're reducing. In other words, this is positive. The electrons go to it, so the electrons can come in here and reduce something. Okay. And then on the other half of the battery, the negative side, that's our oxidation reaction. It's going to lose electrons, so we can go through here and do some sort of work in the middle. Run a motor, light up a light bulb, run your computer. Questions? Okay. So then let's do a practice problem here. This thing actually did that myself without, that's not a problem, and this is a problem. Make this as big as possible here. I may have to make it even bigger. Let's go ahead and read through this problem first. All right, here, I'll do it like this, so you can read with me. Let's make it even bigger. All right, so a chemist assembles a voltaic cell as shown below. One side of the cell contains a silver electrode immersed in aqueous silver nitrate solution. The other side of the cell contains a zinc electrode immersed in aqueous zinc nitrate solution. In this reaction, zinc is the anode. So what's going to happen at zinc? Oxidize, right? And silver is the cathode. So what's going to happen at the cathode? Reduction. Write equations showing the half reactions that take place with this. Okay, so I'm going to want you to write half reactions. I want you to write the full reaction. And if you're sitting around bored, I want you to write the cell diagram. Okay, so I'm going to give you, I'll give you 2 minutes for this. And so I'm going to bring this up so we can just look at that. So what we've got down here is I've got a zinc electrode, right? I have zinc nitrate in solution. Can you guys see how many nitrates there are? How many nitrates? 2. So what's the charge on zinc? +2. Silver nitrate, how many nitrates? 1. What's the charge on silver? +1. Okay? Go ahead and write your half reactions, then add them to a full reaction, and then if you have time, go ahead and draw a cell diagram. Yes?
Okay, is the cell diagram the thing with the lines?
It's the thing with the lines, yes. The cell diagram is a thing with the single line, double line, single line.
Do they need to be stoichiometrically just the straight things?
You're writing as little as possible because you're a lazy chemist not wanting to write more things than you have to.
It doesn't, what is it telling you? Like if you are doing, then what is it telling you?
It is telling, it is a way of describing all of this in as little text as possible. So if you're, let's say you're publishing, and you're an electrochemist, they probably just do that.
Interesting.
Other questions?
Could you scroll up so I can see the list again? Or it doesn't
You don't need to see the words.
Okay.
Okay, I'll tell you, let me help you out though. This is the anode, okay, and this is the cathode. The anode won't always be on the left of these necessarily. I don't know if I'm gonna know better. Does that help? So you're writing the half reactions, write the full reaction, write the cell diagram. All right, who's all the way through their cell diagram? Okay. Why don't we go ahead and work through this then? All right, so I've got to write my half reactions, right? So I've got, so I've got zinc at the anode. So it's going to be what? Oxidized or reduced? Oxidized. So I'm going to go from zinc solid to zinc ions, plus 2 electrons, right? The zinc lost, it became oxidized. It lost these 2 electrons. Then I've got the anode, the cathode side. I'm going to have, if I had oxidation at the anode, I'm going to have what at the cathode? And you always have oxidation at the anode. So I'm going to have reduction. So what we're going to do is, that's where I'm going to have my silver plus we talked about. And that's going to combine with what to make silver solid? 1 electron, right? All right. To do the overall reaction here, I do need to balance this. So I need the electrons to cancel out. So what do I need to do to the silver reaction? Multiply everything by 2, right? Like that. And then I can cancel these 2, and then I can add it together to make my overall reaction that goes zinc solid plus silver ions goes to make zinc ions plus silver solid. Okay? And then, if I want to turn this into a cell diagram, what I need to do is I need to take my anode side. My anode side is zinc solid, right? Goes to make zinc aqueous. They call this the phase barrier because it is changing phase, right? It's going from solid to aqueous. And then there's my salt bridge. And then now I'm going to go on my cathode side, I'm going to go from silver plus goes to silver solid, like that. Okay, and I don't put the 2's in there. That's what you were going to ask about. Writing as little as possible here. Yes, Dakota.
There's silver on the reaction side, but that holds two as well.
Yes, thank you. Yeah, very good. Yes.
How did you know to start with either the solid form of it or the aqueous form?
For over here,
For, like, when you're writing the half reaction, why isn't it the solid and the start for the oxidation and aqueous and the other one?
okay, good question. So how do I know that I start with the solid here? Well, I know the solid forms of the metal have a 0 charge on them. And if I'm going to be oxidizing over here, what's more oxidized, the zinc or the zinc ion? The zinc ion. So I know that I'm going to make, if oxidation's occurring here, I need to put the reduced thing on the left-hand side and the oxidized thing on the right-hand side. And then on the other side, I know reduction's occurring, so I need to put the more oxidized thing on the left-hand side. So I flipped it, and then the more reduced thing on the product side. Is that?
Yeah.
Okay, good question. Other questions? All right. So then let's go ahead and do another practice problem. All right, so this one's a fun one. I'm gonna go, we'll read the words here, but then I'm gonna scroll down to the picture. So after a voltaic cell has been in operation for some time, the appearance of the electrodes changes. So this is our basic zinc copper cell that everybody loves. For example, after a standard copper zinc cell is run for a while, the zinc anode becomes much smaller while the copper cathode becomes larger. At the same time, the blue color of the copper 2 solution fades. We saw this we actually had real pictures of this cell in the last lecture, but we'll just use the cartoons here. Let's get this out of the way. Oh, really, get out of the way. I'm tempted to delete that, but I don't know what I can't remember if I need it. All right, so there's 3 things you need to explain here. I want to give you a couple minutes to do that. Why does the zinc metal go away? Why do you get a bunch of chunky copper metal plating out on this electrode over here? And why does the blue color, copper sulfate is blue in color. I don't think the zinc solution is blue, so I don't know why they drew it like that. But why does the blue color here go away? So written words, 3 sentences. Why do those 3 things happen? Yes.
When you are explaining this, do you have to specify, if you're saying something is getting oxidized, do you have to specify that it is losing its electron, or like if we're supposed to explain something on the exam, or is saying that it's oxidized enough?
You say it's being oxidized, do you need to say that it's losing electrons?
Like, do I have to say both?
Well, if I say define oxidation.
Okay.
But otherwise, if you say it's oxidized, it's reduced.
So
So
like
if
the
the question is written in some way that it looks like I'm testing whether you know that oxidation means you're losing electrons, and reduction means you're gaining electrons, then you want to answer that.
Okay, but otherwise, it's assumed that we know what those mean.
Yeah.
Okay.
Okay, let's go ahead and answer some of these. I'm hoping if I pull this over, it'll go okay. By the way, does anybody run their laptop on Linux? Okay. I'm thinking of switching this to Linux. I'm wondering if I'm going to be sorry in terms of using. I wonder what tools are out there. Anyway, I'll figure it out this summer when it's safe to do so. So why does the zinc metal get smaller?
Because the zinc becomes oxidized and then turned into its ions.
Yep, because the zinc is becoming oxidized to its ions that dissolve in solution. I'm going to say its ion that dissolves in solution. Okay, so it really literally does go away. Why does the copper metal get larger? Somebody else. Yeah, Priscilla.
The metal gets larger because it's being formed from the CuSO4 solution.
Right. So it's being formed from the CuSO4 solution. I like that. What in the CuSO4 solution is it being formed from?
The copper ion.
The copper ions. Right. So the copper ions are being reduced to make copper metal. That I'm going to say plates out on the copper electrode. Or actually, I'm going to say the cathode, which is the copper. It is made of copper in this case. It doesn't have to be. That could be like some carbon electrode or something like that. It would plate out copper on it. So I want to talk about plating. So we talk about plating here. I think I've been trying to decide. I can't tell. I guess, maybe my glasses I could tell better. I'm trying to decide whether my little Roanoke College here thing is raised or whether it's that all the black stuff, it's just the metal here and the black stuff was put on over it. I still can't tell. But in any case, how do they get this on here? Well, let's say that this is just the stainless steel showing through here. It makes the Roanoke College. What they will do, this is black coating here, they will have anodized that on. It's called anodized. So what you're doing is electrochemistry on this. So you put electrodes on here. You put electrodes on and you maybe have a mask here and you dump this in solution and you get this stuff to come onto it, if that makes sense. Right. This is black. I don't know what it's made of for sure. If I had to guess, I would say this is iron oxide. So iron oxide rust. There's two types of iron oxide. There's iron oxide rust, and there's iron oxide that's let me show you. The iron oxide rust looks like this. Okay, and the iron oxide that's this black paint color is this. Is this color. So that might be what this is, FeO. But you would deposit it on there using electrochemistry. If you ever heard of gold plating, same sort of thing. You have a solution that has gold dissolved in it, and you could put a very thin, use electrochemistry to put a very thin layer of gold onto something. Okay, so that was why does the blue color of the ion go away? Somebody else. The blue color goes away because somebody who has an answer. Yeah, Carol.
Because all of the atoms are being used to make the solid.
Yeah.
So the color's going away as ions.
Yes. Yes. So I'm gonna write it a little bit differently, but that's what's going on, right? Because the copper ions are being reduced in solution, the copper ions, and this is our blue color, are being reduced to make copper metal. So we're removing those ions from solution. Does that make sense? All right, let's go ahead and move on then. So let's see. I think we're gonna not worry about this one for now. What I want to talk about is I want to talk about how you add these cells together, how you determine whether things are spontaneous or not using using half reactions. Okay, so we're going to work our way up to that. How do we know? Right, when I look at a lot of these reactions, I actually can suss out which ones I think, whether I think it's going to be spontaneous or not, usually based on what the metals are that are involved, right? I think I've talked to you about this before. You can go to a museum and there are certain metals that over time have lasted, and so you can see them in a museum. So you can see silver in a museum, you can see gold things that are in a museum, all right? You don't ever really see iron things that are made in a museum. I don't know that anybody ever looked for zinc, but you wouldn't find zinc things in a museum either, okay? Because these metals over time, if somebody made that zinc, what would happen is that would oxidize pretty quickly. It would oxidize and it's no longer around for us to see in the museum. This is part of, they blended copper and zinc to make bronze. Bronze, you think about Bronze Age and bronze weapons and things like that. And that way you get something that actually bronze is stable over time. Okay, so, but anyway, what we have is, so we have, when we think about these reactions going on, we can think about half reactions. So this blurry table is from your book. I wanted to grab all of it and I had to shrink it so much on my screen that I couldn't see it. Okay, so I've got another one that we'll use instead. But one thing I want to point out on this table is when we use this table is a bunch of half reactions. And whether these half reactions, whether any reaction is spontaneous or not, is determined based on the difference in volts, which is the potential between these reactions. I'm going to need to go back and define a couple terms in a minute. But since we're here, what I want you to get from this table is we have this reaction right here. I'm going to rewrite it out. Okay, so we've got this reaction here, which is I've got two protons combined with two electrons to make hydrogen gas. All right, and the potential for this reaction is equal to 0. So when we had free energy, and this potential thing is going to work like free energy. We have free energy, and so if I took a reaction and I flipped it for free energy, what happened to the free energy with that? What do I do with the sign to this? I flip it to negative. So what happens when I flip 0 to negative? It's still 0, okay? So I don't know how many hundreds of years ago, they decided that we were going to measure all our reaction potentials, because it really just matters what they are relative to another. We're going to say this is our standard. This is 0, and we measure everything relative to that. It's kind of a poor choice because you have to bubble hydrogen gas through this thing. It's really, if you were to actually use this, which nobody uses today, they use some other one and then they relate it back to the hydrogen electrode. Really difficult system to work with. Maybe somebody wanted to set it and they get a bunch of publications before anybody else could figure out how to do it. I don't know. All right. So how do we know if things are spontaneous? So we're going to use this thing. We've got this hydrogen electrode, which is the basis of everything else, or it's the standard by which we measure other things. But I'm talking about potential. Let's work our way up to that, actually. I should have defined some things first. So I want to remind you that we have this unit called a coulomb. We use a big C for a coulomb. And what that is a coulomb is a unit of charge. All right, so to put it in context for the electrons, I don't know if this is going to be very useful, but it's one electron has a charge of 1.602 times 10 to the negative 19th coulombs, okay? Which I have in my notes, let's calculate how many electrons in a coulomb, but we don't really have time for it based on how things went with the other class. So there's good, but you can tell that, if I've got one of those, I'm going to have to invert this. It's about one time, it's about 10, something 10 times the 19 electrons. So a lot of electrons make a coulomb. Yes?
Will that be a number we have to know?
No. I'll give it to you if you need it. But we're not even going to use it here. Okay? And then on the standardized test, I think all the constants will be there. The equations should be there. But if they're not, it's a standardized test measured against other people. So it's fine. It's all a relative sort of thing, and it will get curved. So that's a coulomb. All right, kind of abstract, right? Because you don't really think about charges and stuff. But you may have encountered amperes or amps. So an ampere is a unit of current. It's a flow of electrons, right? And so an ampere is equal to a coulomb per second. So if we have a coulomb, 10 to the 19th of electrons go through a wire in 1 second, that's an amp. All right, and then finally, what we're going to use in the table below is we talk about volts. Or a volt, or V, is a unit of potential. All right, and so what it is a volt is equal to a joule per coulomb, or joules per coulomb. So what this means is that if I have electrons moving from here to over there, and there's a potential, or if I'm moving from one side of the battery to another side of the battery, how many joules do I get for every coulomb of electrons that move? Okay, and the bigger, so when you think about the volts on your battery, the bigger the volts on your battery, the more joules you get out when they move. Does that make sense? Okay. So volts are what we're going to be concerned about, and volts are potential. And what volts are is this potential thing is like free energy, but it's different in a way that I'm going to specify. All right. When we think about, I like to think about this as a water tower, and I drew a water tower earlier, but maybe I'll skip it this time. So think about it, you've got a water tower, right? What's the purpose of the water tower? Why do we have water towers? What was that? Well, to provide water. Are they just to store water? Why are they tall? When I turn this on, I get water out, right? Is there a pump somewhere that's pumping the water right now? That sense that I turn this on? There is a pump somewhere, but what that pump does is that pump pumps water up in the air into the water tower, and then when anybody in Salem opens a spigot, it keeps that water tower full. When anybody opens that spigot, water goes from high to low, right? Flows downhill. So what this is this is just water flowing downhill from that water tower. Okay, I mean the pipes are all full of water, right? So it's water filling the pipe, and this is coming out. But that's why it's like when you do a siphon, really. Okay, except it's up high. So for electrochemistry, if we think about this, okay, I'm going to give in and draw the water tower. If we draw the water tower, if we think about free energy is the height plus the water. Plus how much water? Right? I can't do any work with this water by letting it flow if there's no water. So it's the height, it's not the height plus really, it's both concepts together, but it's really the height times how much water, I should say. Add a little, okay. It's the height times how much water. When we talk about potential, okay, potential is E. It's the height. Okay, so it is not how much energy. It's a measure of how much energy you could get out, depending on how much stuff flows. Does that make sense? It's going to be important for when we do some things with some equations in a little bit. All right, so how do we actually use, oh, and one more thing. When we have a reaction, so we're going to talk about when we combine two half reactions, if the potential change is positive, that's spontaneous. It's out of the way.
We could have potential differences be, like, are we gonna use for that, or are we gonna use a different?
We're going to use voltage for the potential differences. Was that the question?
Yeah, like I was asking what, I guess, variable.
Yeah, so we worry about potential here. So I'm going to go ahead. Can you guys see these reactions if I make them that big? Can you see that? You get bigger. Bigger. Okay. Let me see. We're going to do it like this. We'll do it big like this. Okay. Just going to make a mess out of everything. All right. So if you look up here, these are our standard reduction potentials. Okay. Now if you look here, this is the actual potential of the half reaction. These are the reactions. If I have, these are all reduction potentials. Okay, so they're all things being reduced. So if I put two things together, I'm going to have one's reduced, one's oxidized, right? So if I want to make the oxidation potential, I flip this. And then if this is the one I'm flipping, what do I do here? I change the sign, just like I do for free energy. You guys with me for that? All right, to make this big, I'm going to run down to the bottom of the page where we can't see the table headings. I'm going to push this out of the way. And I'm just going to make up a reaction with one of these. But I don't like it. I need something else. I need more reactions. All right. I'm going to do I'm going to make a reaction with this and this, palladium and oxygen. Okay. Which one do you want to be at the anode? Just give me one. Oxygen's going to be at the anode. So oxygen's going to get oxidized, right? Okay. So what do I have to do with this half reaction if this is being oxidized? It's a reduction potential right now. I have to flip it. So let's go and flip that one. 2H2O liquid goes to make oxygen gas plus 4H plus aqueous plus 4 electrons minus, right? And I have to, for my potential, well, it's not really a delta because it's not a full reaction. My potential is going to be 1229. Did I get that? All right, volts. Okay. Now we said for the palladium we were going to have that reduced, so it is a reduction potential already. So the palladium, I'm going to go from palladium plus 2 aqueous arrow. Whoops, I'm going to have 2 electrons over here, and then I'm going to make palladium metal. And my potential there is going to be equal to 0.951. I don't need to do anything to it because I didn't flip the reaction. If I want to add these together, You guys with me so far? If I want to add these together, I have to have the electrons cancel. So what do I have to do to the bottom reaction? I have to multiply by 2, right? So this is going to become 4. This is going to become 2. That's going to become 2. And here's a trick. This is really important. It's not a trick. Since this is just about the potential, it's just the height, it's not how much, I do not touch that. I do not multiply that by 2. Okay? And this is the sort of thing people ask you on standardized tests. So I used to be director of health professions advising. I teach biochem, and so I used to recreationally take tests. And it was embarrassing. The last time I took a practice MCAT, this is the only question I got wrong on the chemistry section. Okay. And I got all physics questions right. And I don't know physics very well. So, but anyway, it was embarrassing. So now I need to add these two things together. So don't multiply that times 2 if you multiply your things. That's the upshot there. All right, so I've got water. I've got my electrons are going to cancel, right? So then plus 2 palladium, 2 plus, aqueous goes to make O2 gas, plus 4H plus, aqueous, plus 2 palladium solid. Palladium, not. Is there a P? Well, Pb is lead. Yeah. And then I add these two together over here. And what I get out of that is I get a change in potential now that is 0.278 volts. Okay? Is that, it's negative. I forgot my negative sign. Is that spontaneous or not spontaneous? It is not spontaneous. Because positive, when we talk about electrical potentials, is spontaneous. Okay? So there's a couple tricky little things here. Questions? Move so much faster with you guys than the other class. And you guys ask questions. Yeah.
Why would we not use the PV reaction where we flip the oxygen reaction?
Good question. So why do we flip one and not the other? I had asked you which one was going to be at the anode, right? And so you guys said you wanted the oxygen to be at the anode. So that means this was oxidized. And anytime you see one of these tables, what we were making up a reaction to do, I was trying to take things that were down here because I wanted to use a table we could see what it said. But these are always going to be reduction. You always get a half potential table. It's always the reduction reaction. So you have to figure out, once you know what's oxidized, you're going to have to flip that one, and you're going to have to change the sign.
Reduction always going to be positive, isn't it?
What was the question?
Is your reduction always going to be positive?
Yeah, the reduction potential is always going to be positive. No, that's a good observation. So the piece I took here was from the top of the table, right? Let's go look at where to go. So we can barely read this, right? Because I had to do that. But can you see their negative?
Yeah.
You see their negatives here. Take my word for it. There's some things that are very negative. So it's very hard to reduce. And the example here is, actually lithium is down here at the bottom. So what they're saying is, oh, what happened? There we go. So you can't see, probably can't see it, but it's lithium plus. So it's lithium plus going to, it was lithium plus going to lithium solid. It's very negative. Why would that be a very negative potential? So it's very non-spontaneous. I mean, it's not, by itself, it's not anything, right? You have to compare it to other half reactions. But there's no half reaction we can pull off this table that will make this happen, that make lithium take that electron and become a solid. Why is that?
It's not very electronegative. It's like one of the least electronegative.
It's not very electronegative, and we're about to have, our final that covers both classes, right? Why would lithium want to be plus instead of +1 instead of neutral.
This is the valence electron.
As the valence electrons, it wants to have a full shell, it wants to be like helium. So all the things on the bottom here are like metals going to the solids. Sodium, potassium, okay, it's very spontaneous in the other direction. And that's why if I was to take lithium and throw it into water, there's different things going on. Actually, lithium just kind of fizzes a bunch, but it does spontaneously do that. Sodium's violent enough, I think it has to do with melting temperature or something, but sodium's violent enough that you take hydrogen gas and it lights on fire. Potassium's even worse, okay? Potassium, watch some videos on the internet. There's some fun videos where people are throwing these in. I think I told you guys, I did some fun demos with this before they told me I couldn't do demos anymore. Yes?
Is there like an oxidation table, like how the reduction and reaction table, or just this?
Are you asking, is there an oxidation table?
Yeah.
No. You will always only be given, I've never seen anything but reduction potential tables, and you make them the oxidation reactions by just flipping them and flipping the sign. Is there another question here, I thought? Okay, well, we've got 3 minutes. Let's see if we have another good practice problem here. I've had a lot of practice problems, but we didn't get to many of them. So one of these will probably be great. Let's try one problem if I can get it out and we can look at it soon enough. I think the problem for us here, there we go. Oh, come on. We didn't already do this one on the bottom. So here we're using these potentials, right? What I want you to do is write out what those half reactions are. And then figure out what the potential is for the full reaction. All right, to do that, I'm going to have to actually scroll up and pick them off real quick, okay? But if we think about, I'm going to go ahead and I'm not going to write out the half reactions to show them to you. I'm just going to write what the potentials are. So we've got to do copper and we've got to do silver. I'm just going to write the reduction potentials down. So copper's got to be somewhere here down the bottom. Maybe. I'm not seeing copper. You can go ahead without me. You can go ahead and start writing those things without me if you got enough down, but you probably didn't.
Is
Yes.
the thing that, or is the element that has the, I guess, more positive, or I guess larger electric, or the potential difference value, sorry, excuse me, is that one gonna be the one that, like, does that help you determine which one's the anode and which one's the cathode?
The actual, let's do this. I'm not going to be able to find these potentials fast enough for you guys to do anything with it. But related to that question, this tells you what's the anode and what's the cathode. This formation here. So write out what the half reactions and full reactions are for this. This is the anode. This is the cathode. Period. Okay. And we won't add the reactions together. I'll leave that for the homework because we've got a minute left at this point.
So,
Yes.
look at the
Don't worry about the potentials. Just write out with the time we've got, which is almost nothing. Write out the half reaction and write out the full reaction if you can get to that. Now we've got a minute left here. Let's use it. Okay, and so what this would be then is we'd have copper solid, right? For the full reaction, you should end up with copper solid plus 2 silver aqueous are going to go to, we need a new pen one of these days. It's going to go to copper 2 plus, it's trying to stop me, plus 2 silver solid. That would be your full reaction is what you would have ended up with. Okay?
Okay.